Before watching this video, you should know that this is actually a segment of a larger video series called the Ultimate Linear Algebra Guide, where I cover each concept more in depth with larger videos and have problems and solutions attached to each video that you can work through. The resource is completely free, but the videos themselves are a little bit longer, so it takes me a while to make. Go ahead and check the description if the linear algebra guide video for this corresponding concept has already been released. And if it has, go ahead and check it out because it is the better resource. Otherwise, until it does, you can stick around and watch this video. Make sure you subscribe and turn notifications on so you'll know when I do release the corresponding Ultimate Linear Algebra Guide. And with that, we can get into the video.
Okay, so we already explored the case with no solution, so now we're going to move on to the case with infinite solutions. Over here, once again, I got two systems of equations, but this time they have infinite solutions. So at this point, I think that you should be somewhat comfortable with Gaussian elimination. It's okay if you're not perfect, but I want you to pause this video and try solving these systems of equations on your own. We're going to first go over this system, so solve this system and come back to the video when you're done and just check your answer. I'm going to do it myself as well, but this is more to just make sure that you're getting it and you're in a good position if you can solve the system on your own. Okay, so let's go ahead and let's make this a matrix. This column would represent the coefficients of x, so 1, 2. This column represents the coefficients of y, 1, 2 again, and this would represent, we would add on this column to represent what these equations are equal to. So x plus y is equal to 2, 2x plus 2y is equal to 4. Okay, cool. So now let's go ahead and let's apply Gaussian elimination to this matrix. So the first leading one is already created for us, so let's create the second one. But to do that, we need to eliminate the first entry in this row. So we go up this row and we see that there's a leading one above it. So we can add 2 times this row, or sorry, subtract 2 times this row from this row in order to eliminate this term. So let's do that. We would subtract 2 times row 1 from row 2 and change row 2 in our final matrix. Doing that gets us 1, 1, 2 in our first row because our first row doesn't change. We're only affecting our second row. 2 minus 2 is 0, 2 minus 2 is 0, and 4 minus 4 is 0. So here we arrive at the case of infinite solutions because this writing the equations from bottom to top like we're supposed to gets us that 0 is equal to 0 as our first equation. Now, this is obviously always true. We're never going to encounter a case where this isn't true, no matter what our variables are. This is always going to be true. So here we have infinite solutions. The difference between this case and the case with no solutions is that in our case with no solutions, this entry right here was a non-zero number. We had that 0 is equal to some non-zero number, which is obviously never true, and would yield us with the case of no solutions. But since this is always true, this gives us the case of infinite solutions. Okay, now, in an Algebra 2 class, it might have been enough to leave your answer like this and say that this system has infinite solutions. But in linear algebra, we have to take it a step further and describe the set of infinite solutions that this system of equations yields us. To do that, we need to create something called a free variable. We have to set one of our main variables equal to this free variable. Remember, we have 2 variables in the system. The first column represents the coefficients of the variable x. The second column represents the coefficients of the variable y. We set the free variable equal to the the variable in the column with no leading one. What that means is, well, let's just check. Here we have a leading one for x, but for y we have no leading one. Well, you might say, but Rithvik, this is a leading one. That's not the case. This right here is not a leading one because it's not the first non-zero entry in this matrix. If we had a 1 over here, that would be a leading one. But this isn't the first non-zero entry in this row, so it can't be a leading one. Here, we have no leading one in the column for y, so y becomes a free variable. We only do free variables in the case where there is infinite solutions. In the case where there's no solutions, we can't really describe a set of anything, so we just write no solutions and we end it there. But in the case where there's infinite solutions, we can create a free variable. So to set y equal to a free variable, we just mean that y can be any real number and it will still satisfy our system of equations. So to do that, we would write this: y is equal to t, where t is some real number. So all we're really saying here is y can be any real number and it will satisfy this system of equations. Since we've described the solution for y, we can do the same for x. So for x, we can use the first equation. Remember, we have to write the solutions from bottom to top. So we can use the first row. We get that x plus y is equal to 2. But we know that y is equal to t, so we get x plus t is equal to 2. So now we can solve for x. X is equal to 2 minus t. And any real number t will satisfy this system of equations. So these are the solution to this system of equations. And there's infinite solutions because we can use any real number t and use these two equations, and it will satisfy this system of equations. Now, you might be a bit confused on the whole deal with creating a free variable. So we're going to, of course, we're going to practice with the 3x3 system here. And after that, you'll obviously practice on your own using the problem set. So hopefully you'll be a little bit more comfortable with it there. But the idea is to just set the column with no leading ones variable equal to t and just use that as a way to create an infinite set of infinite solutions. Okay, let's go on to the second system of equations. Here we have a 3x3 system. Once again, I encourage you to pause the video and try solving the system on your own. At this point, I would expect you to at least be able to start a solution using Gaussian elimination. I think we've done enough examples that that's viable. Go ahead and try solving the system and using Gaussian elimination to reduce it to row echelon form on your own. And after that, you can come back to this video and see my solution. Okay, let's solve this system. Let's go ahead and create the matrix. Here we would have 2, 2, 1, 2, and 6. -1, 1, 1, and 0, -1, 0, -3, and -6. So the reason we have a 0 here is because there's technically a plus 0 y in this equation, but we don't write it because it's kind of redundant. But we need to include it in our coefficient matrix because we have an entire column for y, which is this column right here. So we just put a 0 there in order to signify that this equation doesn't have a y term in it, but it technically does. It's just a y term with the coefficient of 0. Okay, so let's start by creating our first leading one. So to make this 2 a leading one, we can divide this entire row by 2. So 1/2 row 1, and we're going to try and change row 1 in our final matrix. So let's do that. 2 divided by 2 is 1. -1 divided by 2 is -1/2. 2 divided by 2 is 1. And 6 divided by 2 is 3. So, and we're only changing our first row, so -1, 1, 1, 0. Row 2 stays the same. -1, 0, -3, -6. Row 3 stays the same since we're only changing row 1. Okay, now let's move on to row 2 of our matrix. First, we need to eliminate all the non-zero terms to create. Well, we need to eliminate all the non-zero terms before what we want to be our leading one. So we need to eliminate this -1. To do that, we can add row 2 and row 3. So row 2 plus, well, we go up this column, we see that there's a leading one here, and we need to do something with this leading one, and if we add these two together, we get 0. So we do that. So row 2 plus row 1, and we want to change row 1. Cool. So doing that gets us 1 minus 1/2, 1, and 3. So that's the first row. The second row is -1 plus 1 is 0. 1 minus 1/2 is, well, it's positive 1/2. 1 plus 1 is 2. 0 plus 3 is 3. And the last row stays the same because we're only affecting the second row of our matrix. Okay, let's move on to creating the second leading one. To do that, we can multiply the entire second row of our matrix by 2. So 2 times row 2, and we want to replace row 2. Doing that would give us 1 minus 1/2, 1 and 3, since the first row stays the same, 0, because 2 times 0 is 0, 2 over 2 is 1, 2 times 2 is 4, and 2 times 3 is 6. I'm just multiplying this row by 2. The last row, once again, stays the same because we're only affecting the second row of our matrix. Okay, so we've created the second leading one. We can move on to creating the last leading one. To do that, all we need to do is eliminate these two terms first and then make this a 1. So we take this, the term we need to eliminate, we go up the column and we see that this is the leading one. If we add these two rows together, we should eliminate this entry. So let's do that. Row 1 plus row 3. So row 3 plus row 1, and we want to change row 3 in our final matrix to eliminate this term. So 1 minus 1/2, 1, and of course 3, because the first row stays the same, 0, 1, 4, 6. So minus 1 plus 1 is 0, just like we wanted. 0 minus 1/2 is minus 1/2. Minus 3 plus 1 is minus 2, and minus 6 plus 3 is minus 3. Okay, so now we can eliminate this by adding 1/2 row 2, because minus 1/2 plus 1/2 is 0, and we need to make this a 0 entry to create a leading one here. So let's do that. Let's add 1/2 row 2 to row 3. So row 3 plus 1/2 row 2, and we want to replace row 3. So the first row stays the same. Can do a bit better than that. Minus 1/2, 1 and 3. I am getting a bit better with writing on a computer. It's a little bit different, but I guess I'm getting a little bit used to it. The second row stays the same. And the third row, well, we add half row 2, so 0 plus 1/2 of 0 is just 0. Minus 1/2 plus 1/2 is 0, just like we wanted. Minus 2 plus 2 is 0. Minus 3 plus 3 is 0. So once again, we arrive at the case where we have an entire row of zeros. With the system of equations with no solution, this term wouldn't be equal to 0 to be some non-zero number, like let's say 3 or something. But here, since we have an entire row of 0, the row of the coefficient matrix plus the entry in the column we added on are all zeros. So since we have all zeros, we get the last equation to be 0 is equal to 0, which is always true, and this system will have infinite solutions. Just like the 2 by 2 matrix up here. Let me just go over to it. Here, we once again had the case that 0 is equal to 0, so even there we had infinite solutions. Now, just like the 2 by 2 matrix, for any system that has infinite solutions, we need to be able to describe the set of infinite solutions. So let's do that. Let's first go ahead and figure out which column which variable doesn't have a leading one. So let's go down x. It seems as though there is a leading one for x right here. Y has a leading one because this is the first non-zero entry in this row, but Z doesn't seem to have a leading one. This isn't a leading one because we have some non-zero entries before it, so it can't be a leading one. If we wanted Z to have a leading one, then this term would not be equal to 0. But since it is, Z is the variable we need to, but since it isn't, Z is the variable we need to make our free variable, because it doesn't have a leading one in its column. This isn't a leading one, this isn't a leading one, this isn't a leading one. For Y, this is a leading one, and for X, this is a leading one. So let's make Z our free variable. We have to make Z equal to any real number. So to represent that, we set it equal to T, where T is just some real number. Now, since T is just some real number and we set Z equal to T, we can use that in our other two equations. So we write equations going up. For the first one, we get that y plus 4z is equal to 6. Well, we know that z is just t, so we can write y plus 4t is equal to 6, and we can solve for y by moving this over there. So we get y is equal to 6 minus 4t. This is our solution for y. This is our solution for z. We can move on to solve for x. Here we can write out the equation x minus 1/2 y plus z is equal to 3. Here we know what y is equal to, and we know what z is equal to, so we can substitute that in to solve for x. So we get x minus 1/2 times 6 minus 4t, because that's what y is equal to, plus t is equal to 3. So x minus 3t, or sorry, x minus 3 minus, or plus 2t rather, because we just distributing, minus half times minus 4 is plus 2, and plus t, which is this term right here, is equal to 3. Solving for x gets us that x is equal to 6 minus 3t. And this is our solution to all of our variables. It's perfectly fine that we have t here, because t, as long as z is equal to t, we can substitute that in to solve for y and x, and this satisfies all three equations. You can check this to be true by setting z equal to 2 and solving for y and x, and showing that whatever you get for y and x satisfies all three of these equations. I'm not going to do that here because I know the solution is correct, but that's a way that you could verify your solution on an examination or something similar. Just substitute in t to be something, and you get solutions for all three variables, and you could use those three solutions in this system of equations to show that they satisfy all three equations.